Okay, so we are back again to another video where we are looking at mathematical proofs, and now we are going to look at the proof by contradiction. If you are still new to this channel, hit the like button and subscribe for more content like this one. So we are going to look at proof by contradiction. This is one of the most important mathematical proofs in maths. Also followed by proof by mathematical induction, etc. So with this one, what we're doing, we assume something that we know that is false to be true. So we assume, when you're making a hypothesis, you're going to assume to be true something you know is false. So that's the basis of proof by contradiction. So here we are just proving that a statement is true by showing that its opposite leads to a logical contradiction. So I'm saying we are proving that a statement is true. You're proving that a statement is true. You're proving that a statement is true by showing that its opposite leads to a logical contradiction. Leads to a logical contradiction. Okay, so this is best defined using an example. So I'm just going to dive right straight to an example to show you how you can apply proof by contradiction. So example, we are given a statement, root 2 is a irrational number. So we are given the statement, root 2 is an irrational number. Root 2 is an irrational number. So now we need to prove that the statement is true using proof by contradiction. So first of all, what do? When you apply proof by contradiction, so you're going to make a hypothesis. So you're going to assume that root 2 is rational. Right. So we are going to assume that root 2 is rational. Remember, the statement said it's irrational, but we are going to assume that root 2 is rational, which means we are assuming the opposite. We are assuming the opposite. And then, so from here, so how do you prove this one? So we are just going to say there exists. We're going to take an advantage of the arithmetic way of proving this. So there exist integers. Let's just say there exist integers a, b, right? Where b is not equals to 0, and we are saying the highest common factor of these integers is equals to 1, which means such that root 2 is equals to a over b. remember, when you're talking about rational numbers, when you, based on the fraction aspect, these are just simple fractions that they have decimals that terminate, right? Or they have recurring decimals with the same value. So those are rational integers. But when you're talking about irrational integers, these are irrational numbers. Sorry, when you're talking about irrational numbers, these are numbers that have recurring decimals that don't terminate, isn't it? So in our case, we are assuming that since root 2 is rational, it's going to form a function. It's going to be formed by two integers a and b, such that a over b is equals to root 2. And we are saying, in order for a over b to be rational, we are saying the highest common factor of a, b should be 1, and also b should not be equals to 0. So from this aspect, remember, we are saying there exist integers, which is a and b. So from here, we are going to square both sides, such that we have 2 is equals to a over b squared, which is equals to a squared over b squared. So from here, we can rearrange this to a squared is equals to 2b squared. So since they have the highest common, since both numbers have the highest common factor, which is 1, so from here I can just say if a square is even, then the base is also even. What does this mean? So if a squared is even, then a is even. We proved that earlier when you're proving using direct proof. So I'm going to use this property that if a square is even, then the base is even. So if a squared is even, that means a is even. So from here, we know that an even number we represent it using 2k, right? So now we are going to come back here. So we're going to have, instead of a here, we're going to have 2k squared is equals to 2b squared. So from here, you have 4k squared is equals to 2b squared, which we can see that b squared, when you simplify this, we're going to get b squared is equals to 2k squared. So from here, now we can also state the same thing, that if b squared is even, then b is even, right? Then b is even. So what does this mean? Now automatically we can see that from this point we have also represented b in this format. We also represented b in this format. So now we can see that a and b are both even, right? And b are both even. This contradicts that the highest common factor of a and b is equals to 1. So therefore root 2 cannot be rational, which means root 2 is irrational. Okay, so what have we done here? So here we are given a statement that root 2 is an irrational number, and then we want to prove by contradiction. So when we're proving by contradiction, we assumed the opposite way, but you assume that let root 2 be rational. So when we are saying root 2 is rational, so we took two integers, we define two integers a and b such that b is equals to 0, is not equals to 0, and the highest common factor of a and b is equals to 1, such that the fraction, such that root 2 can be represented using those two integers. And in order for this statement to be true, we are saying b shouldn't be 0, right? And then also the highest common factor of a and b should be 1, since we are assuming that the root 2 is a rational number. By doing this, we squared both sides, and then we made a squared the subject of the formula. Once we made a squared the subject of the formula, we can see that if we said if a square is even, then its base is also even. Whereby now if a square of a squared is even, then automatically a is even, which is something that you can prove using direct proof. So from this statement, automatically we're saying a is even. We know how we represent an even number, so a is going to be equals to 2k, where k is a member of all real integers, right? And 2k is equals to, so 2k squared is equals to 2b squared, and when you simplify that, you're going to get 4k squared is equals to 2b squared, and then if you further simplify that, b squared is equals to 2k squared. So from here, b is squared again, right? So b squared is represented in terms of in terms of k, and we know that k is what? Is a member of all integers. So from then we can state the statement that b squared is even. If b squared is even, then b is also even. So now we have proven that a and b are both even, and these statements will contradict the fact that the highest common factor of those two numbers is 1. Therefore, root 2 cannot be rational, which means root 2 is irrational. So we prove by contradiction. So that's the basis of proving by contradiction. So this is the third mathematical proof that we've discussed so far. So with the next proof, we are going to look at mathematical proof by induction. This was proof by contradiction. So stick for the other video so that you can learn more about mathematical